All right, so continuing with our introduction to complex numbers, I want to start with looking at how to evaluate expressions such as these with or without our GDC. For example, this first one, 3 minus 2i squared. We can quite quickly do this without a GDC. It's just a perfect square binomial, so we'll have 3 terms, 3 squared, which is 9. The middle term will be 3 times negative 2i twice, so you'll have negative 12i for the second term, and the last term will be negative 2i times itself, which is positive 4i squared. I'll write it like that at first. And then though, keep in mind that I squared is the same as negative 1. So this is really the same as 9 minus 12i minus 4. Write all like that. And collect like terms, you have 5 minus 12i. And while that isn't very time consuming at all, I also would encourage you, in fact, it's kind of essential that you're familiar with your GDC, and you should be able to just type this in as is, and within a second or so, you should be there. And so, while this is not difficult, it is more or less just tedious as the powers get larger and larger, and that's what calculators, in my opinion, are meant to do, this tedious, mundane, routine calculations. And so this here, I would encourage you just to use a GDC, although you could figure it out in the way as before, and you should get really quickly negative 9 minus 46i. Same thing for this last one. This would be really quite unpleasant to do by hand with the GDC again. It takes just a moment. You should get negative 597 minus 122i. So again, always be familiar with your GDC. Generally, it's probably faster than doing these by hand, aside from maybe this one here. All right, so the main thing I want to talk about in this lesson is an Argand diagram, which is another way of visualizing a complex number. So in an Argand diagram, we visualize a complex number as a vector on a two-dimensional plane, where the x-axis represents the real numbers. Actually, I'll just write RE. And the y-axis represents the imaginary part, because recall, a complex number has both a real part and an imaginary part. So, for example, if I look at A, it says here A represents, on the Argand diagram, a complex number. And so the coordinates of A, if we just look on the plane here, are negative 2, 4. So the x-axis, that's the real axis. So that means this represents a number that has a real value of negative 2. The y-axis is the imaginary axis, which in this case is 4, which means this number has negative 2 as a real number, as well as positive 4 times I for the imaginary part. And so this is visualizing the number negative 2 plus 4i, and that's A. Maybe I'll write that over here. And whereas B, notice, is entirely on the x-axis, or I really should say the real axis. And so while this has coordinates of 5, 0, that means this number represents 5 as a real number, plus no imaginary numbers. So really, just 5. So this is the number 5. All right, C we'll get to in a bit. Notice C is not on the location of point C is not on both the x and y are not whole values, so we'll get to there later. All right, so now I want the absolute value of A and the absolute value of B. Well, recall perhaps from long ago that absolute value, while in practice just makes things positive, it really represents the distance of a number from 0. And we're dealing with real numbers. Absolute value is always quite straightforward because the distance on this axis here of a number from 0 is just either the distance to the right or the distance to the left. And so hence, when dealing with real numbers, absolute value is exceedingly simple to evaluate for the most part. Just if it's positive, nothing changes. If it's negative, you make it positive. However, once you look at complex numbers, their distance from 0 is still not terribly complex, but it's not always a horizontal line. And so, for example, if I want to find the absolute value of A, which is also called the modulus of A, you want to be familiar with both notation. It's just the distance, the diagonal distance from point A to the origin. We can just use the Pythagorean theorem a squared plus b squared equals c squared. So in this case, it's going to be that distance. So the square root of, there's a few ways of looking at it. I'll write -2 squared. I'll just take the actual x coordinate, square it. It doesn't really matter if I have a positive 2 there, plus 4 squared. And we should get exactly root 20, which we could simplify to 2 root 5, should we wish. So that's the absolute value of a. The absolute value of -2 plus 4i is 2 root 5. Or the modulus of a is 2 root 5. Same idea. We want to be, again, familiar with both. Whereas for b, since it is just a real number, the modulus of b, or the absolute value of b, I can just see the distance from there to there is 5. So I could use the Pythagorean theorem, but that's kind of a waste of time, in my opinion. Okay, so now let's look at point C, or complex number C, which the coordinates of, it seems like it's at -3 on the y, but I can't tell exactly what it is on the x. So I want to find the argument of a and the, oh, I'm getting ahead of myself. I'm not looking at C yet. Before I get to C, I want to look at the argument of a and the argument of b. Sorry, I forgot to mention that. The argument is a measure of the distance, sorry, I shouldn't say distance, measure of the rotation, measure of the angle in standard position from here to here. If we're looking at complex number A. And so to find that measurement there, I can just realize, okay, I can just find the measurement from here to here, which is 180 degrees. We can think in radians as well, but I'll stick with degrees for the most part right now. Take away whatever that angle is there. And that angle there, I can figure out using some pretty basic trigonometry. And so what I'm going to do to visualize this is I want to find that theta right there, which I can use the inverse tangent function, because I can imagine a triangle here with a height of 4 and a width of 2. And so that angle theta I put there would be the inverse tan of 4 over 2. So the argument of A, which is that angle again, we tend to write ARG. Actually, I should have a lowercase. ARG of A. I'm going to calculate it with 180 degrees minus the inverse tan 4 over 2, or just 180 degrees minus the inverse tan of 2, and I get 180 degrees minus 63.435 degrees. And again, 63 degrees roughly is that angle right there, that reference angle if we think about trigonometry. And I'll write this to 4 significant figures. That means the argument comes to 116.6 degrees. And again, while we could do this in radians, since this is an SL lesson, I'll for the most part focus on degrees, because radians are technically just part of the HL course. And so the argument in general, it's, again, the angle in standard position between this initial arm here and wherever the vector lies. And we always keep the angle either from here to here, so between 0 and 180 if it's in the first 2 quadrants, or from here to here between -180 and 0 if our vector is, if our complex number, however you want to look at it, is in the 3rd and 4th quadrants. And so for the argument of B, since it is right on the x-axis, again, nice and pleasant, the argument of B is just 0. 0 degrees, 0 radians, whatever. So those terms, modulus and argument, we will be hearing a lot going forwards, and they're not terribly difficult at all. It's perhaps easy to forget. Modulus, same as absolute value, that's a distance. Argument is an angle in standard position. So you want to recall that this sort of range, we don't want to say, for example, we don't want to use, for that angle from there to there, we don't want to use something above 180 degrees. We want to use something between -180 and 0, which now I can start to talk about angle or complex number C. So in Cartesian form, complex number C is -3 root 3 minus 3i, so which means I now know the coordinates of this point. So this point is at -3 root 3, comma, -3. Or if I write -3 root 3 as an entire radical, I get -√27, comma, -3. Same idea. All right, so what we want to now find is the modulus and argument of this. I'm going to start with modulus. Modulus, or absolute value, is that distance from there to there. And again, I can use the Pythagorean theorem. I can know the distance from here to here is 3 root 3, or root 27. That's the distance. The distance from here to here is 3. And so I can use the Pythagorean theorem, root 27 squared plus 3 squared. And so we get exactly 6 for that. So the modulus of C, or the absolute value of C, is the square root. I'll write it as, I'll go back to the minus 3 root 3 all squared plus 3 squared. We should get root 36, which is exactly 6. The argument of C, and I kind of touched upon this a moment ago. If I look back at my visual, I'll erase all this. It has to be, we have to look at this angle from here to here by convention. So it's going to be a negative angle. It's going to be, I can estimate it, but I want to be exact. So I'm going to think of it like this. I'm going to think of it as, I know that's negative 180 degrees plus whatever this angle is right here. So again, I want to find that reference angle, which again, I can figure out using some basic trigonometry. In this case, if I look at this triangle, I'll draw it up here this time. It's all kind of the same thing. I have a height of 3. I have a horizontal distance of 3 root 3. And so if I want to find this angle here, it would be the inverse tan of 3 divided by 3 root 3. So it's going to be negative 180 degrees plus whatever that angle is, the inverse tan of 3 over 3 root 3, which while we can use our calculator, I hope we can also realize, especially HL students, that that reduces to the inverse tan of 1 over root 3, which should sound familiar. The inverse tan of 1 over root 3 is exactly 30 degrees. So this is a special angle. I have 180 degrees plus 30 degrees. However we look at it, we should get an argument of negative 150 degrees if we're thinking in degrees. And especially for HL students, it is important that we recognize ratios like that as being one of our special angles. Although again, we are allowed to use it, GDC. All right, last question. I have one last complex number, and I've been very creative and worked my way up the alphabet to D. So D is a complex number such that the modulus is 4 root 2 and the argument is negative 45 degrees. On the grid, I want to sketch the diagram and I want to write the number in Cartesian form. So I'm going to actually start with the argument, because negative 45 degrees, I can see, must look something like this. And in fact, 45 degrees is a slope of 1, or in this case, negative 1. So I know it must look something like this. I just don't know how long it goes. So I'll just kind of draw that for now. But I know that there must be negative 45 degrees. So there's the argument. The modulus is 4 root 2. So how do I know where that point is? I need the distance from here to here to be 4 root 2. So that's all that's left. So let me get rid of these points and let's figure that out. Ideally, we can realize that, maybe I'll draw it down here actually. So if I have a triangle, ooh, that's a really messy line. Let's try that again. That's a bit better. If I have a triangle like this, and I know this angle here is 45 degrees, and I know this is a right angle, which means this must also be 45 degrees. And hopefully we quickly realize this is a special triangle. And remember, one of the basic ways of remembering special triangles is if these two sides are both 1, this is root 2. However, this hypotenuse is not root 2, it's 4 root 2, which means I just got to visualize this exact same triangle, but everything multiplied by a scale factor of 4, all the measurements 4 times more. So these are both units of 4. Means I now know where this vector ends. I know it has a length and a width of 4, so that's pretty easy to show. That is right, negative 4 comma negative 4. So now here's my Argand diagram for complex number D. So that's the first part of the question done. Writing this in Cartesian form, well, I know the coordinates are 4 comma negative 4. So now I know this must be the same as 4 whole, the real number 4, plus or negative 4 times I, or 4 minus 4I. So D equals 4 minus 4I. That's Cartesian form. And again, we were given the modulus and the argument, all of which we will see many times going forwards. Nothing's inherently difficult about it, as long as we remember basic trigonometry and working with radicals, but there's a fair number of new terms, and we want to be familiar with those as quickly as possible.